Welcome to our presentation on the Spaghetti Bridge project. In this video, we'll explain our bridge design, the materials and construction process, and the testing and results. The main objective of this project was to design and build the lightest possible bridge that could carry the greatest load before failing. According to the project requirements, our bridge had to span 350 millimeters, be no wider than 80 millimeters, and weigh less than 200 grams. The bridge needed to rest freely on two roller supports, and only spaghetti and Quick-Sellers super glue were allowed as materials. The project allowed us to test how spaghetti behaves under different structural forces like tension, compression, and bending, helping us apply theoretical concepts we learned in class into the real world. We started the design stage. Our group looked at a few common truss bridge types. However, the Pat truss design stood out because of the way it manages internal forces. In a Pat truss, the diagonal members are under tension and the vertical members are under compression when the bridge is loaded from the top. This makes it a very efficient and stable design under the type of testing we were doing. Another reason we chose the Pat design is that it allowed us to reinforce key areas where tension and compression forces were the greatest. This layout made it easier to balance material use, for example, adding more spaghetti strands to the lower tension cords and using fewer where the forces were lower. The triangular arrangement of the Pat truss also provided good structural symmetry, which helped with even weight distribution and reduced bending moments to the bridge. We also had an alternative design that we considered, which was the Warren truss design, which we considered because of its simplicity and use of evenly spaced triangles which distribute loads efficiently. However, after researching and watching several spaghetti bridge examples online, we realized that while the Warren truss performs well, it doesn't handle concentrated central loads as efficiently as the Pat truss. For building our spaghetti bridge, we used a few key materials that met the project requirements. The main structural material was Barilla Spaghetti No. 7. We chose this band because it has a consistent diameter and is strong enough to represent real structural members when bundled together. For bonding, we used two types of Sellers super glue, the fix and go version for smaller joints where we needed quick drying, and the Power Grip adhesive for larger and reinforced connections that required extra strength. During construction, we also used rubber bands to hold bundles of spaghetti tightly together while gluing. This helped us keep the strands straight and evenly aligned until the glue set. Finally, rulers and secateurs were used to make sure every member was cut accurately and matched the scale. To begin construction, we bundled around 15 spaghetti strands using rubber bands for each cord and secured them with Sellers glue, aligning them straight to form uniform beams. This was done to ensure the spaghetti strands were formed together, making each member strong. These glued bundles were then left to dry completely before assembling to ensure rigidity and prevent bending. These bundles were our vertical diagonal members as well as our top and bottom cords. The base of the bridge was built first. We measured and cut 4 bundles of spaghetti for the longitudinal beams at 400 millimeters long. We then proceeded to add 5 cross beams evenly spaced at 100 millimeter intervals, which made the width of our bridge 80 millimeters. These were glued together using Sellers super glue, which dried quickly and helped us keep the members straight and aligned. Once the base was complete, we attached the vertical members to give the bridge its height, followed by the top cords which connected verticals. This formed a rectangular frame on each side. After that, we installed the diagonal members, which are the most important parts of the Pat truss design. They were glued carefully between the top and bottom cords at 45 degrees to help distribute the weight evenly. Once both sides of the trusses were finished, we joined them together with horizontal cross beams to form the full 3D structure. The entire process required patience and precision, especially since spaghetti is fragile and can snap easily, but by working carefully and reinforcing each connection, we ended up with a stable structure. This is our trial bridge testing video.
I only have 15.
As you can see from the video, when the load is applied slowly at the center of the bridge, it managed to hold up 13.5 kilograms or roughly 132 newtons before failing. The failure was sudden and happened along the bottom chord of the bridge between points C and D. We observed that cracks began forming when the spaghetti strands first The bundled strands started to split under tension when the glue joint gave away. This told us that the tensile strength of the spaghetti itself was exceeded before the glue actually failed. Essentially, the spaghetti stretched and snapped while the adhesive bonds were still holding. This kind of failure made sense for Pat truss design under the central load because of the bottom chord members are the main tension members. They experience the greatest pulling force as the top chords are being compressed. Even though our child bridge performed well, supporting around 54 times its own weight, we knew there were key areas for improvements. Firstly, the bridge was too heavy, exceeding the weight almost by 50 grams. That reduced our weight to load ratio. Secondly, the bottom chords were not strong enough in tension, which led to the early failure. To fix these issues, for our final design, we made several engineering adjustments based on what we learned. We increased the number of spaghetti strands in the bottom chord members from 15 to 20 strands to make them stronger and prevent the same tensile rupture from happening again. At the same time, we needed to reduce weight somewhere else, so we reduced the strands in the top chords and diagonal members since those parts were mainly in compression and didn't require as much material. We also reduced the number of strands in the vertical members from 15 to 12. This is our final bridge testing video.
Still going big slow. It's not supposed to be seen.
So as you can see, our final bridge performed better after the changes were made. We managed to hold 15 kilos, which is higher than our trial bridge that broke at 13.5. Even though the final bridge is still a little over the weight limit, it was lighter than the first one and carried more load. This failure happened though because of buckling in one of the diagonal compression members instead of snapping in tension like before, which means the load was shared more evenly and the design was more balanced overall. The adjustments were made like adding extra strands to the bottom chords and reducing spaghetti in other areas, which really helped improve its strength to weight ratio. Thank you.